Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is Absolute and Conditional Convergence Revisited, a Deeper Dive. As always, please be attentive while watching this video. By way of introduction, in this lecture we revisit, in a slightly more general and deeper dive, two important concepts, and these are distinct types of convergence. Absolute convergence, which is the more powerful type of convergence, and conditional convergence, which is a weaker form of convergence. Now, we're not just doing this to be doing this, we're doing this to prepare for an appropriate treatment of the gold standards for convergence testing, the ratio test and the root test. Stay tuned for these two important and soon coming attractions. So let's go back to the definition. A series, the summation of A sub n, is called absolutely convergent if the summation of the absolute values of the A sub n is convergent. If the summation of the A sub n is convergent, and the summation of the absolute value of the A sub n's is divergent, the series is called conditionally convergent. Here's a fact. This is actually a theorem. We'll talk about the proof. So if the summation of the A sub n is absolutely convergent, then it is also convergent. And that means it converges, and that even means it converges conditionally as well. That means that this series is convergent, and so if it's absolutely convergent, that forces the series to converge. So let's look at the proof of this. So first notice that the absolute value of A sub n is either A sub n or is minus A sub n, depending on its sign, sign. This means that we can say that if we take the absolute value of A sub n and add it to A sub n, that will be at lowest 0, and it might be as big as 2, the absolute value of A sub n, depending on if the A sub n is positive or not. Now, since we're assuming, that's the if part in our theorem, that the summation of the absolute value of A sub n is convergent, then this summation of 2 absolute value of A sub n is also convergent, since we can just factor out the 2 out of the series, and 2 times the finite value, the limit, will still be finite. This, however, allows us to use the comparison test up here, and so what we're saying is that this is less than this one converges, so does this, that the summation of A sub n plus the absolute value of A sub n is also a convergent series. So we can write the summation of A sub n, which is what we're going to have to claim is convergent, is equal to, and we're basically adding and subtracting the same thing. So this is a summation of A sub n plus the absolute value of A sub n minus the summation of A sub n. So these two things will cancel out, and so that means that this is the sum of, and in fact in this case it's the difference of, two convergent series. So it is also convergent. This fact is one of the ways in which absolute convergence is a stronger type of convergence. You see series, if they're absolutely convergent, then they have to be convergent. However, series that are convergent may or may not be absolutely convergent. And in fact, relative to that, you may recall that we have already shown previous lectures that the alternating series does converge, but is not absolutely convergent, because if you take the absolute value of each term of the alternating harmonic series, you get the harmonic series, which we know does not converge, and we have a couple of proofs of that. So these are the examples that we're talking about here. Let's do some examples, and again, these examples are illustrations, so you want to study them now or go back and try to redo these, and then you can look at the answers, but these are good learning exercises. So here what we're to do is determine if each of the following series are absolutely convergent, conditionally convergent, or perhaps divergent. So we have problems A, which is the summation n equal 1 to infinity minus 1 over n. B, we have the summation n equal 1 to infinity of minus 1 whole to the n plus 2 all over n squared. And in C, we have the summation n equal 1 to infinity of the sine of n over n cubed. Okay, so let's deal with the first one, which was this one. Now, this is the alternating harmonic series, and we saw previously, and this was on the lecture on alternating series, this is an alternating series, and it satisfies all the conditions of the alternating series theorem and the alternating series test. So this is a convergent series. So we don't need to check that here because we already proved it. But let's see if it is an absolutely convergent series. And to do this, we need to check the summation n equal 1 to n of the absolute value of that. But when you take the absolute value of each term, what happens is this minus 1 to the n always is going to be 1 over n, and this is the harmonic series. And we know, actually we know several proofs that the harmonic series is divergent, and so we have shown an example that this one is conditionally convergent, but not absolutely convergent. Here's the second one, and so we can also check here that this is absolutely convergent, because if I take the absolute value of this, that will drop out this minus 1, and that'll become 1 over n squared. But this is a p-series with n equal 2, so we know that this converges absolutely, and that means we don't have to even bother checking the convergent because we get that for free. That was a consequence of the theorem that we just proved earlier in this lecture. And we're done with this example. Okay, the last example here is a summation n equal 1 to infinity, the sine of n over n cubed. Well, if we just look at the, just to check to see if it's absolutely convergent, then the summation n equal 1 to infinity of the absolute value of the sine n over n cubed is equal to the summation n equal 1 to infinity. This is the absolute value of sine n over n cubed, because the absolute value of n cubed is n cubed. Now, the sine of n, whatever that is certainly between minus 1 and 1. We know that from our trigonometry, so that means that the absolute value of the sine of n is less than or equal to 1. So we can say that this term, which is the general term in our series, is less than or equal to 1 over n cubed. But we know this 1 over n cubed, the summation n equal 1 to infinity of 1 over n cubed, converges because it's a p-series with p equal 3. And so by the comparison test, we know that this also converges. Since this is absolutely convergent, then it is also convergent. So none of those diverged, I guess. Okay, now we're going to review another thing, and we're recapping a topic that I talked about earlier in an earlier lecture. When we first discussed convergence of series in detail, we noticed that we can't think of a series as an infinite sum because some series can have different sums if we arrange their terms. I gave you an example of that. I didn't prove that. In fact, we gave two arrangements of an alternating harmonic series that gave different values. That's actually the example that we did. But now we're going to close off this series by describing this test, and we're also going to prove this test. So, given the series, the summation of a sub n, if the summation of a sub n is absolutely convergent and its value is s, then any rearrangement of the summation of a sub n will also have s. You see, it's robust to rearranging the terms. You'll get the same answer. The other thing that we looked at was, and this is called number 2 here, if it is conditionally convergent, meaning it's not absolutely convergent, and r is any real number, then there is a rearrangement of the summation of a sub n whose values will be r. This is kind of an amazing fact, and this is sometimes called the Riemann rearrangement theorem in honor of the great mathematician Riemann. He's the same Riemann that you studied in Calc 1 when you were talking about Riemann sums. Okay. So now when we have the tools under our belt to determine we can make a few more comments. First, we showed in an example earlier that the alternating harmonic series is conditionally convergent, and so no matter what value we choose, there's some rearrangement of the terms that will give those values, and we in fact illustrated that with an example. Note as well, this fact does not tell us that the arrangement must be only that it does exist. It doesn't tell us what it is. Next, we showed that this one, which is minus 1 to the n plus 2 all over n squared, is absolutely convergent, so it doesn't matter how we arrange it, it will always converge to the same value. In fact, it can be shown, and maybe I will show this in this course, I don't know if I'll have time or not, but the summation n equal 1 to infinity of this alternating series is minus pi squared over 12. Now, to summarize this before we look at the proof, in Bradley speak, absolute convergence is very powerful, totally trumping conditional convergence. Conditional convergence is far less powerful, and in fact, it is incredibly fragile. You just change the order and you can get a totally different number. In an earlier lecture, I gave you an example illustrating point 2 with an example, but now in this lecture, as a closing part, I'm going to outline the proof of both of these conditions. And I'm going to restate the theorem just altogether. So again, if something is absolutely convergent, then any rearrangement results in a new series that is also absolutely convergent to the same value. It doesn't matter what order the terms are in. If something is conditionally convergent, then for any real number C, there's a rearrangement of the series such that the new series will converge to C. And again, that second part is an amazing result. All right, so let's go through the proof. So suppose we have the summation from n equal 1 to infinity of a sub n is absolutely convergent. Then the sequence, and this is a partial sum Sn, is equal to the sum of the absolute values up to n converges. That's what this means. In particular, it is bounded because the absolute value is less than k for some number k. You see, it converges, so that means eventually this sum gets close to some number k. And this is an increasing sequence also because, I guess I didn't say that, but it's increasing because all of these are non-negative. So it's a bounded increasing sequence. And so that's we know that it converges. If we take any rearrangement of the terms, we can form a new sequence. I'm just going to call this Tn, and this is these j's are j sub i's, mean I'm mixing up these. Then this is again is bounded by the same number k. But since all terms in the partial sum T sub n are positive, the sequence is monotone increasing. Therefore, this one is monotone increasing. Therefore, it must converge. It remains to show that the limit of the rearrangement is the same as the limit of the original series, and it says that's left as an exercise, but this is simply saying that the limit of a convergent sequence is unique. Finally, suppose that the series, the summation n equal, so that completely proves part 1. Part 2, suppose that this summation n equal 1 to infinity of a sub n converges conditionally. Then we know by the divergence theorem, and actually we've already proven this, we proved that early on, we know that the sequence of general terms converges to 0, so the a sub n converges to 0. We know that it does not converge absolutely because we said it converges conditionally. That means it doesn't converge absolutely. Since the sequence of partial sums of absolute values is increasing, it means that the series of absolute values must converge to positive infinity. You see, if it did converge to a finite number here, what you would get is you would get it would be absolutely convergent. It's not, and since they're positive also, and since they go to 0, it cannot not converge. And so it converges to positive infinity when we take the absolute values. There must be infinitely many positive terms among the aj, or otherwise you never get to positive infinity. So we call them bj and collect them to form a series, and the new series must converge to positive infinity again. And you can think through that. There must be infinitely many negative terms also. We'll call them Cj and collect them to form a new series that must converge to negative infinity. They're all negative, and you can think about these whys. So now the idea of the proof is, and the details are left as an exercise. Now these details involve some adroit juggling of epsilons and deltas, and that's not really a focus of Math 2232 at the College of DuPage. At the College of DuPage, you were trying to make engineers who aren't afraid of math and can do the math that's required for their engineering studies. At Princeton, they're teaching mathematicians calculus 2, and that's a little bit different, and epsilons and deltas are more appropriate there. Okay, so this is, the details are not here, but the general idea is. So collect enough of the B sub j's such they add up to a number that's just bigger than C. And then add as many terms from Cj as necessary to make the resulting sum just less than C. So you see you're getting close to the, and again add B terms to just bigger than C, and then add terms Cj that are just less than C, and so on. So we'll bounce back and forth, and eventually we will get the sum is C. Then you can show the resulting arrangement of B's and C's forms a sequence that converges to C. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.